makes sense. Like, I'll have to implement that. Right.
Teaching, professing, MIT 101.
All right, great.
Me too. Cool. Okay, welcome back. Let's get started because I have like 40 pages of notes here and there's no way we're going to get through it. But I want it to go slowly and carefully, and if I don't get through it all, life goes on. I had one more, when I was planning it out, I had even one more thing on the end, and I just realized it's not going to happen. Okay, so let me actually start. You guys okay? Wait?
Yes?
Yes?
That's good.
Let me actually start with a quick fix from last time. I slightly overstated what LQR was doing, and I apologize. I don't know if you guys saw me, even when I was walking in last time, I was kind of scratching my head because as I was deriving the example, I thought it was too extreme. But anyways, I had said that LQR is amazing. It is amazing, but the particular example I gave you was a little too dramatic. I said because you can if you were to search over the control parameters k directly, then you might even find yourself, in the wrong set of stable k's, that there's these disconnected sets. The example I gave you, I just made an algebra error, and actually the set of of stabilizing k in this example is the pink region. I had flipped it. Okay, and actually the reason I was scratching my head is because I sort of knew that had to be wrong because, in fact, so the fact that it's a very non-convex set, true. Disconnected, not true. So LQR is not quite as amazing as I said. The sets become disconnected in the output feedback case, which we'll see later. But let me just apologize for that mistake in the last lecture. And it'll be correct in the notes. So, good? Yes?
I have a question with that particular drawing. So we said that there doesn't exist a P and Q matrix such that every point in that stable set is covered by LQR or something like that.
So you know the P and Q version of this? Is that because I didn't say that last time, did I?
Yeah.
Right. So, and that's exactly why it has to be connected. Actually, is if you know the derivation through the quadratic form P and Q. That's why the P, it's convex in P and Q, in PQ, and since that's a invertible mapping, that it has to be somehow a continuous mapping. That means that this has to be a connected set. So that's exactly the proof. Okay, but that's last time. We're on to the new stuff. Okay, so. Last time we talked about LQR as balancing even these pretty underactuated systems like a gymnast with no wrist torque on a high bar or the cart pole, right? That LQR actually did a good job of stabilizing those, and even the linearization did a surprisingly good job of when we took our nonlinear vector field of the pendulum. Right? This was theta versus theta dot of the pendulum, and we made an approximation. Where do I think chalk go? that we actually got a pretty darn good approximation with linear control, right? In the vicinity of the fixed point, it was doing the right thing. And then, of course, when you get away from the fixed point too far from the place where you've linearized around, the vector field could be arbitrarily wrong. We know that it should be 0 here, but it's actually predicting something like this. So my goal for today is to handle the rest of the space. And we'll do it it'll be very satisfying for the pendulum. It'll still work for the cart pole and the acrobat, although it'll make you scratch your head a little bit more about that probably. And in general, I hope it's a bit of it's going to be a sort of a throwback. Okay, there was a time when the way you, there's my picture. There was a time that when if you were a nonlinear control theorist, you would spend lots of hours scrutinizing the equations of motion of your plant, let's say, of whatever you're trying to control, understanding maybe from mechanical intuition or other things some of the properties of it, and then deriving controllers which you could verify algebraically, on pencil and paper, right? And that time is mostly gone. There might even be people on the campus that would yell at me if I said that. But mostly it's gone, and mostly that's replaced with numerical approaches. That I'm a fan of many of them, and optimization has made a lot of things happen. But the problem with the optimization approaches is that this skill of having mechanical intuition about your system and setting it up, it's sort of a lost art, right? So I'm going to try to introduce tools that we're going to use in our algorithms. But I want to give you a little bit of a throwback into what it was like to have to find the equations that prove stability inside your plant, because it matters. I think the problem is you could write optimization problems that are just silly if you're not thinking about the mechanical system you're trying to control. And so having a little bit deeper understanding of the mechanics and how it implies some of the algorithms matters. Okay? And I'm going to do it through the language of Lyapunov functions. So if you know Lyapunov functions already, hopefully it'll still be a graphical and interesting introduction to it. But it's important that we get the details right, because it's going to form the basis of the next set of algorithms that we're going to write. Let me actually also say, so today we're really going to sort of be a throwback to, let's call them hand-designed control. And I want to say something about this. So the controllers we're going to write down today, they are not going to be optimal. We're not going to use optimal control to derive them. Okay, but in many cases, they're actually going to be better. So, what do I mean by that, right? So, I'll try to make it clear by the end, but make sure you call me on it if I don't get back to that. But it's fine to use optimal control, but don't put it on a pedestal. It's only as good as the objective function you've chosen to optimize. The objective functions, for instance, that we've chosen to optimize so far, that we have good tools for optimizing, don't capture everything. For instance, they haven't yet captured the uncertain. If you had uncertainty in your plant parameters, if you didn't know the mass or the friction or something like that, how well would they perform? They don't capture robustness. These aren't going to capture it explicitly, but if you start putting it on real systems and realize that you don't actually know where the friction is, you're going to find that in many cases these are less sensitive to the equations of motion being exactly accurate than these. Because they were not derived from optimization can actually, if you optimize a specific objective, it might take you to some peak that could be at odds with robustness if you're not careful. So it's an important point. The total goal is to formulate optimization problems which capture the things we care about, including robustness. And we'll get there as far as we can in the semester. But today you're going to already see, if you were to type these in, you're going to already see a little bit of a disconnect there. All right, so if they're not optimal, if they're not optimizing some objective, then how are we going to know that they work? Are we going to have any satisfying, I mean, I would love to say, here's the sufficiency theorem. I'm going to show you that this is a good controller by producing a cost-to-go function, and then we'd satisfy it, right? If that's not going to be available, then how are we going to somehow say that the controller we write down is any good? Well, we're going to use the language of stability instead. Instead of optimality, we're going to show that the controllers we generate are at least stable. Okay? Good. So in order to do that, we need some more tools. So I'll start with the example that I think is clear, but there were details that we brushed over when we did this before. It's amazing how, even the most advanced algorithms, you can really kind of go back to a 2D example and understand a lot. So, let's consider the case of ML squared theta double dot. It's plus MGL sine theta. And then minus b theta dot. So there's no control input right now, but just some damping, okay? So, of course, b is greater than 0. Now, I can't integrate the equations of motion in closed form. That's how I introduced the class, right? I can't actually integrate this to tell you what theta is as a function of time, but I'm pretty sure that we'd like to have the ability to say that theta goes to 0 as time goes to infinity, right? How do we actually prove that? And it turns out it's kind of it requires a surprising amount of machinery to prove it, right? And the trick is ignore the details of how theta evolves with time, and look at something that has a more simple dynamics, which in this case, for this system and for many systems, is the energy. So if we, instead of looking at theta, we look at the total energy in the system. Then we can write it down. 1/2 ml squared theta dot squared minus mgl cos theta. So I've got it, being negative at the bottom just to, it's okay though. And what I'd like to do is think about how does that energy evolve with time, right? So I can do that by just taking the time derivative of the energy. I can do that with, I get, the 2 cancels out, so I get ml squared theta double dot times theta dot. Use the chain rule on that, okay? Minus mgl sine theta, theta dot. I get a plus here. Theta double dot, though, in fact, ml squared theta double dot was this term over here. So I'm actually going to insert this right there. Is that okay? So that's going to be theta dot times negative b theta dot minus mgl sine theta, and then plus theta dot mgl sine theta. That's nice. This term and this term cancel out, so I just get negative b theta dot squared. And if you're a mechanical person, then that's, okay, that's what I should have gotten, right? That's, if you think of this as a torque, that's torque times velocity. That's what you'd expect to have energy go down as torque times velocity. Okay? Negative b theta dot squared. What's important is since b is greater than 0, theta dot's mostly greater than 0, right? So this is, this whole thing is less than 0. Sorry, theta dot squared, right? Is less than 0 whenever theta dot is not equal to 0. Okay, so that, the intuition here is that energy is going down. We also know that energy is bounded below. It can't go below negative MGL cosine theta in this one, which is just negative MGL is the lowest it could possibly go. So we also know it's going down, it's got a minimum. So you'd like to say, okay, well, I'm going to get to the minimum. But it's a little subtle still, right? There's one other thing. What's to say we don't get stuck somewhere else with theta dot equals 0, my energy stops going down, and I never get to the bottom, okay? In fact, what are the set of states? There's lots of states where theta dot equals 0, right? Here's one, here's another one, right? In fact, this, if you were to plot this, right, I've got theta versus theta dot. This is the energy. It looks like, this is a negative function that, see what I'm trying to draw there? Right, it's, whenever theta dot equals 0, it's like this, but there's a whole line of places where theta dot equals 0. Okay? So it needs a little bit more work to prove that it actually gets to 0. And the key idea here, the one extra piece we need to know, we need to use, solutions, read that as trajectories. There are only a few trajectories of the system for which theta dot is always 0, right? So almost all these trajectories that they might visit theta dot equals 0, like if I have one that's going like this, and then instantaneously as I'm changing direction, theta dot equals 0. But even though I'm there for a minute, for a moment, then I will move away. Okay, so the whole trajectory is going to experience this e dot less than 0, right? And it'll eventually drive myself down, with the exception of the fixed point at the bottom, where e dot could be exactly 0 and stay exactly 0, or the fixed point at the top. This, if I were to prove that this thing converged to the bottom, then you should be suspicious, right? So there's a fixed point at the top, which is a trajectory that can stay there forever, accumulating e dot. E dot is going to be 0 there, and indeed, it'll stay there, and that's one fixed point. This is the other fixed point. But any other place, even though it may visit, instantaneously have e dot equal to 0, will eventually have e dot being negative enough that it'll go down and come to the bottom. So we're going to have the machinery to say that carefully. So theta equals k pi, where k is an integer, are the only invariant sets I'll define that in a second. E dot equal to 0. Okay? An invariant set is one that if you start in the set G, then you'll stay in the set G. Okay? So if x is in G at time 0, implies that for all time greater than 0, x is going to stay in G. That's an invariant set of my dynamics. Once I'm in this set, I'll never leave. It doesn't change. Okay? So the fixed point at the bottom is an invariant set. The fixed point at the top is an invariant set. You can use the language saying what's the largest invariant set, which would be a collection of all the fixed points. Okay? Right? But these are the only invariant sets because the only invariant sets with E dot equals to 0, because this other one, even though E dot equals to 0, there's a bunch of them, it doesn't stay there, it's not invariant. So if you put all that together, then you can ultimately prove that E is going to go to MGL cos of this, which implies that theta is going to go to this, and theta dot is going to go to 0. That's the structure of the argument we needed to just prove that this silly little pendulum is going to get to the bottom or to the top. And we're going to now do that in the more general case. Okay? And it'll even be I think it'll even be clearer in the general case where I don't have to talk about periodic fixed points and the like. Okay, so Lyapunov functions are just the generalization of this idea. That's all they are. So mechanical energy for the pendulum is a good idea, but what if you're watching the stock market or some other dynamical system that doesn't necessarily have a mechanical energy analog? Can you find an energy-like function that could prove something about the long-term dynamics, right? So if you have x dot equals f of x, and you want to prove, let's just even keep it simple, we'll prove the stability of the origin. I'm going to prove that x equals 0 is a fixed point, okay? Then you can do that if you can come up with a function we'll call it v of x, and I'd like it to have the properties that for all x that are not equal to 0, just for simplicity, you don't actually, you can move these around, but I'm going to just, for simplicity, say that it's always going to be greater than 0 when x is not equal to 0, and then equal to 0 when x equals 0. Yeah?
In this analysis, is the inverted pendulum considered stable?
All that I've been able to prove is that if you let time evolve, when you look at it later, eventually as time goes to infinity, you're going to be in one of the fixed points. Right? It does not say that, it says that the set, which is all of the fixed points together, is stable. Okay, so if I can produce some function that's positive everywhere, right? And it has the time derivative, which is partial v partial x, f of x. I'd like to have that this has the properties that for all x not equal to 0, v dot of x is less than 0, and v dot of 0 equals 0. Right? This is just my energies going down statement. And in this case, it's simpler. It doesn't have these, it has only one fixed point to worry about, okay? There's one other condition, which is that you'd like to have radial unboundedness. Which is that b of x goes to infinity as x goes to infinity. You want to make sure it keeps going up. Otherwise, you can produce screw cases where you're getting, v dot's getting smaller and smaller, but you're moving farther and farther away from the origin. So that's unusual that you actually need that, but it's important. If you can do this, if you can produce this, then you have as t goes to infinity, v goes to 0, and in this case that implies that x goes to 0. So it's proving global asymptotic stability. And this v is the Lyapunov function, of course. Okay, so this v, what I wrote here gave a statement that says as t goes to infinity, x goes to 0, which is asymptotic stability. That's the definition we gave of asymptotic stability. You can also use Lyapunov functions to talk about exponential stability, or, not surprisingly, stability in the sense of Lyapunov, right? You can also, there are variations of it that will prove something about, you can talk about the local, you can use Lyapunov functions for local stability, global stability, or even regional stability, which would be stability over some specific region. Okay? And we're going to do that. So the picture you should have, right, is simple. In the simplest diagram, if I were to say that trivial system here, if I have my flow on a line here, which is just saying that this fixed point is stable, what it's saying is, give me a Lyapunov function, just like a potential function here, which is something like this. You could think of it as you can think of this system as just like an overdamped marble in a bowl. There's a potential function. And how does the mechanics of that work out? If I were to prove this is stable, the standard choice would be to choose x squared. V dot of x, which is partial v, partial x, f of x, is now 2x x dot. Which is less than 0, apart from at 0, right? So that proves that this is globally asymptotically stable. We happen to know more about the system. A linear system we know is actually exponentially stable. How would we use a Lyapunov function to argue exponential stability? So it's less than 0 for all x not equals 0. What was the difference between exponential stability and asymptotic stability? Asymptotic stability says you're going to get there as time goes to infinity. Exponential stability says you get there at some rate, that you're going to get closer and closer to it at some rate, right? So how would you do that here? Well, you'd want v dot to maybe not just be less than 0, but be less than some proportional amount, right? So the variation for global exponential stability, if all those conditions hold, plus I actually have v dot of x is less than some negative alpha of v of x. Which is true in that case. Alpha is 2, right? Alpha, of course, has to be positive. Why is that true? Is because then you can say roughly that if you think of v of x of t, you know it's going to be less than or equal to, if I were to integrate this, this is like think of this as a simple differential equation in v. So I know that the solution of this has to be less than or equal to v of x0 e to the negative alpha t, which is what I needed to prove exponential stability. What about stability, some global statement about global stability in the sense of Lyapunov? What's the tweak on this condition? Less than or equal to 0, right? If I could only say v of x is less than or equal to 0, then it's stable in the sense of Lyapunov. Okay? All I get to say there is that if v dot of x 0 is equals to c, I know that for all t, v of xt is also less than or equal to c. I don't know it goes to 0. And in fact, that's what you need. Do you remember this? The definition of ISL was that you pick a delta, I pick an epsilon. Okay? And so this is exactly why you needed what you needed in that game. Right? Was this, let me think of x1, x2. Let's say I have some Lyapunov function that has contours like this. So this is my v of x equals some constant contours. Okay? The statement that I made, that we needed for Lyapunov stability, was to say that if x0 minus my fixed point is less than delta, then there exists some epsilon. So for all t, x of t minus x star is less than epsilon. So sorry, you pick the epsilon. You say, I want to make sure I stay inside this circle. I get to pick a delta to guarantee that that's true. So if you pick this circle, you say, I want to make sure that I'm always this close to the origin. Then what do I have to pick? I have to pick a delta, which is, oh, look at that, I lined it up pretty well. So a delta which so this is, I know if this is a contour of the Lyapunov function, that if I start inside there, that I'll stay inside there. Which means I have to pick delta to be on the inside of that one. So anywhere I started in here, this is my delta ball, means that v of x is going to be less than this constant. Since I know that it can never leave the region, it'll always stay less than epsilon. And in fact, for any epsilon you pick, I'll be able to pick a delta by just looking inside that. Okay, so these Lyapunov functions are expressive and powerful. Okay, so You can also do it locally, regionally, or globally. So for local stability, you only need v dot to be less than 0 or whatever variation of it in some ball around the fixed point. Right? Because the local ISL only said that you pick an arbitrarily small epsilon, I'll pick an arbitrarily small delta. So as long as this as long as you can find something that in the vicinity of the fixed point, v dot is less than 0, you can say something about the local stability using the Lyapunov functions. Okay? For global stability, you have to have it hold everywhere. Except for the origin, but this part of the condition. For regional stability, it's a little bit, you have to be a little bit more careful. Regional stability, it needs to hold over some invariant set. Or rather, for if I pick a region, right, whatever region I pick to prove v dot's less than 0, it doesn't actually prove, if you were to pick this pink region, it doesn't actually prove something about that whole pink region. Some of these leave, you know, maybe v dot goes up over here, and since this orbit could leave, it could go off forever. It only proves for the largest invariant set inside. But it does say something about in here, the interior. So for regional stability, you want v dot less than 0 over some invariant set. And a standard one that people pick is, for instance, you have an invariance proof by having v. You could say an invariant set would be v of x less than or equal to some rho. That would be you pick a contour here. Any one of those contours is an invariant set if v dot holds inside it. So those are good candidates to choose to say something about regional stability. In fact, if you have this, this also implies that this set, can I call it G? Implies G is the region of attraction or it's at least inside the region of attraction of X star. A lot of definitions, but hopefully they make sense. Like I said, it's going to matter. If you ask an optimization algorithm to prove v dot is strictly less than 0 for a system that has frictional impact, it's not going to be able to give you an answer, right? So the differences between these matter. one more example just to make sure that lands here. If let's say x dot equals negative x plus x cubed, which is one of my favorites here. It looks like negative x at the origin, and then the x cubed term comes up and wins. Remember we plotted this before. We know that this one's the fixed point, stable fixed point. We also know that this is the region of attraction. Okay. We know that graphically, but we can also use Lyapunov to prove that. Okay, so if I choose v of x is just x squared again, then what can I say about that? V dot of x equals partial v partial x f of x, which is 2x times negative x plus x cubed, which is negative 2x squared plus 2x to the fourth. It's a little easier to write that as negative 2x, or 2x squared, x squared minus 1. How about that? So x squared minus 1 is negative around 0, and then it catches up. This one is always positive. So this function is less than 0 for all x, not equal to 0 inside negative 1 and 1. At 1 and 1, it becomes 0 again. Right, the function v of x looks like this, and v dot of x looks like this. So this is 1, negative 1. If you plot v dot of x, you'll see something like this. It starts going up, and it goes up fast once it goes up, okay? But it's less than 0 in here, 0 here, 0 here, 0 here. So if I say, for all x where v of x is less than 0 here, right, then this actually proves that this set is the region of attraction. Does that make sense? Yeah.
Does it tell us about fixed points also?
Does this one tell me about exponential?
Fixed points. Like, can I say that if v dot x is 0, then those are fixed points?
If v dot x is 0, it does not necessarily apply that's a fixed point. It says, because, if you have v of x going up, energy dot was 0 even at non-fixed points, right?
Like here it is, but it's not in general.
Correct. In the plane, I think it actually is true, like in the 1D examples, but the pendulum's a counterexample for once you get to 2D. The argument that we invoked in order to prove stability, saying that we go to the largest invariant set, is the last piece of machinery that I'll sort of rattle off here, which goes along with Lyapunov functions. Sorry, go ahead.
So for energy function for a damped pendulum, it's not a Lyapunov function that shows that it's asymptotically stable?
Good. Exactly right. So far, we've only been able to say, we would only be able to say it's stable ISL. And the last piece, that argument we made about, well, it doesn't stay in some place and accumulate 0, is the last piece of machinery we need, which is called LaSalle's theorem. Right, which says that if you have v of x only less than or equal to 0, right? Then in general that proves only stability ISL. But LaSalle's theorem says it also proves that you will converge to the largest invariant set. It's one extra thing you can say.
For something like the pendulum, how do you figure out which invariant set is larger?
This is the math getting in the way. The largest invariant set is the accumulation of all the invariant sets, right? So that's sort of a cute way to say it. But since every one of those sets by themselves is an invariant set, the largest invariant set is actually the set that includes all of the fixed points. People get that? Yeah. That's actually all this proves. So the only thing it says is that you will get to the set which contains all the fixed points in that case. All right. There's one more really fundamental question that you should be asking yourself right now, which is, we talked about cost to go functions, and this seems like a different tool chain or something. How does it connect to cost to go functions? And it's actually really simple, and really, I think it really clears things up, okay? So, relationship to dynamic programming, okay? So the Bellman equation was min over u g of xu plus partial j partial x f of xu, right? That's what we spent a lot of time with. And I tried to help you see this as thinking of that as just that's the rate at which you go down the cost to go when you're being optimal. And it should be that, so if I for the optimal u, if I'm acting as well as possible, I can insert that optimal u here. What it's saying is the dj dt star is negative, that I'm going downhill at the rate that I can accumulate cost. That was the HJB solution. So it's frustrating to use because in order to make this, verify this statement even, I have to somehow solve for J, which is solving a PDE, right? So that condition is a hard thing to check. By contrast, what are we doing with Lyapunov functions? We're just saying this, whatever variation you're saying. Okay? So because we've changed that equality into an inequality, it's easier to certify. You're more likely, this one, you know, here you can often guess a V. It's so much less restrictive. Or you can guess a controller. And you will see some examples here of you guess a V and then that sort of takes you through the steps of figuring out what a controller could be. Right, now, if you choose G, well, you get to choose your cost function when you're doing optimal control, right? If you happen to choose a G that's always greater than 0, then your cost to go function is also the Lyapunov function. Okay? Which makes sense, right? So if the Lyapunov function is just something that goes downhill all the time, right, then the cost to go is something that I should go downhill all the time, so it should be a valid Lyapunov function. And it is, by all the selections I've made today, it is when G is positive. If there's ever a place where you get reward instead of cost, then you could go there and you could go uphill, right? But we don't give reward in control theory, only reinforcement learning people do that. Okay, so there's a close relationship here. This is just loosening this equality constraint to a sufficient, saying this is enough to prove stability. This is required for optimality. This is enough for stability. Yeah?
So this is using the Lyapunov to say that when we choose our optimal, it is stable? Is that what you're saying?
Correct. If your G is always positive, then your optimal controller is also stable. That wasn't even the point I was trying to make as much, but it's a good point. I just want you to, in both cases, you're trying to find some function over the state space that talks about the long-term dynamics, that summarizes the long-term dynamics. In this one, you need to find a very specific one, and it gives you great power. It says not only this is the best function, and I've proven optimality. But if you just want to talk about the long-term dynamics, you can ask for less, and it's much easier to work with these. So in places where we have to give up on this, we can still do this. All right, so let's put it to work. Oh, sorry, go ahead.
I was just going to ask, what are some good strategies for guessing?
We're going to see a few. And oftentimes, mechanical energy is a good, anytime you can connect it to mechanical energy or even intuitively. We're thinking converging. So someone in the initial survey was saying, well, let's think about proving the convergence of first order optimization methods using some of these tools. They use Lyapunov functions, for instance, and typically you end up thinking about that as having like a mechanical analog, or even if you want to think about least squares as putting springs between your data points and your solution, and then it's the solution is the thing that optimizes the potential energy of the springs, right? That comes to rest. There's for non-physical systems, you can often put physical intuition into them, and energy is great. Okay, so let's get the pendulum to the top instead of at the bottom, and see if we can do it with a little help from Lyapunov. Okay, so here's the big idea is leveraging, again, a little bit of insight we have about the pendulum. And that's that this eyeball thing is a pretty good idea, pretty fundamental thing about the system. Right? This is an unstable fixed point of the undamped, uncontrolled pendulum. And this thing, we called it the homoclitic orbit. And it's this sort of magical orbit. It's not so magic, but it's the set of states for which, if I get myself to this, I can just ride that. It'll take me to the unstable fixed point, right? So the intuition we'd like to have is we'd like to build up a Lyapunov function that's at the minimum here and gets bigger as you move away from the orbit. Okay. So I'd like to prove that the system converges even, you know, it seems like it should be enough to prove that the system converges to that orbit, and then that orbit will make me eventually visit the fixed point. So we'll make sure we understand what the implications of that in a minute, but that, as an intuition, I think that's good. So, you know, the goal is to swing up to the top. Including with small torques. So not just inverting gravity, right? And the key idea is drive the system to the homoclinic orbit. Okay. So how is that orbit defined? That's an orbit. This line is a line of constant energy. These are the energy contours of the system, right? So in fact, it's the one where the total energy is just MGL. So let me call that, I'll use my little superscript D for desired. Okay, so my desired energy is MGL. I'd like to figure out if I'm at some other place with some other energy, how do I drive myself to that desired energy? Okay, let's think about the driven pendulum here. I'll leave damping out for the first pass, but it's easy to add. So for this, the energy dot is just negative U theta dot. Sorry, it's U theta dot. It's exactly the same, but when U was negative V theta dot, I got negative V theta dot squared, right? E dot is just this, if I were to do that exact same math I did before, right? Just torque times velocity. So here's my proposal. Let's choose a Lyapunov function. V of x is, I put a half in front of it to keep it simple, E of x minus E desired squared. Yeah? I'll just say that I'd like to somehow drive the system to this, so I'm going to make a quadratic form in energy that goes up away from the desired energy. Okay? So what is V dot of x? Chain rule, I just get E dot of x, which is U theta dot, times this error, I'm going to call this term E tilde. Okay. Just my error tilde. And this one I can go ahead and stick in U theta dot. And I'll write it like this. Okay? Now my game is, I get to pick U. That's the name of the game, right? I'm designing a controller. What would I pick if I'd like to make this thing less than 0? A perfectly reasonable choice would be to pick, for instance, negative k theta dot times E tilde, which implies that V dot of x is now negative k theta dot squared E tilde squared. Okay? Just like before, this thing is going to be less than 0 as long as E tilde is less than 0, or is not equal to 0, and theta dot is not equal to 0. So marching through the same logic, this is going to prove that the system converges to the largest invariant set, which in this case is now going to be, it's going to be 0 when E tilde is 0, which is on that manifold, or any, and the invariant sets that include theta dot being 0, which is fixed points, right? So that controller is not going to pull me away from this. I'll accept that there is a set of measure 0 that I'll never get away from. But if I'm even just a little bit away, then V dot's going to start going down, okay? And it's actually going to converge to this one. Yeah?
How do you let it move in a way that it moves to the
Yeah? So you're saying how do I know that it doesn't go back to here? Yeah. Right. So it's the fact that this thing is going to go down. You're right, but I think with a little bit of thinking, you could see that the Lyapunov function only tells me it goes to one of those two, but it's going to go always to the other one because you're adding in a thing that's proportional to the distance. As the only reason that is that theta dot was 0. So I think a simple, I think a simple analysis shows you that it's going to go in that direction. What's the simplest way to do that? You could probably, I mean, you could show that V dot is going to go in that direction, or the energy is going to go in that direction. Another way to do it is to type it in. Well, so let me ask another question, though, as this is loading back up. Does this stabilize the fixed point at the top? Is the resulting controller going to be stable at the fixed point on the top? It's actually not enough to stabilize the top in any of the senses that we've talked about. Because a small perturbation here in this direction will cause you to go all the way around. Right? So right now, this strategy stabilizes this orbit. Okay? So it'll take me here, but if someone knocks me just a little bit here, it's going to go all the way around like this. But we already know, so we're going to do one extra thing. We already know how to stabilize in the region around this. So let's switch to the LQR controller once we get to the top. Once we get near the top, I'll turn on LQR. And that can then stabilize this fixed point. Okay, so this is that controller. The only reason it's that many lines is because it has both the LQR and the energy shaping, but the energy shaping controller here is, a couple lines, super easy to type in. And I'll just run it a bunch of times and plot the resulting orbits. Okay. They all start pumping up energy and go to the fixed point. You'll find little kinks here for when the LQR controller turns on, where it switches. because the control might change discontinuously there. So you'll see a little kink, and then it goes sunk to the origin. How did I decide when to turn on the LQR controller? I used the level set of the cost to go from LQR, because I know that that's a Lyapunov function, okay? And in fact, I can prove, we'll have the machinery later to prove that 2 is a reasonable choice for that. So once I get inside the 2 level set of the LQR controller, I'll turn that one on and let it drive me to the goal. Okay?
So if you're outside of 2, would you just wait until the M3 was at 2 and do that?
Yep. And in fact, 2 is not the optimal choice, but we are going to be able to find a pretty good approximation of what that threshold really is. Okay, so this is kind of, like I said, this is the way, maybe one way to do controls that isn't as common anymore, but is this sort of manipulating the equations to get something that proves my Lyapunov function works, right? And the Lyapunov function sort of made these interesting candidates. And there's some subtlety in picking this. I could have picked something else that was always greater than 0, but might have had very large gains. This one has a nice property that it actually stabilizes even if k is super small. As long as k is greater than 0, it's going to stabilize, right? So what's the difference there? So if k is really small, I'm just going to pump really slowly, right? But it means it's going to work even if I've got severe torque limits, right? It'll just take a long time. It'll eventually get up around and go, I'll keep going downhill. Okay? If I had my energy dot, if I had damping in here, and my energy dot looked like this, then I could have just added that I could just reverse damping in my controller too. I could just add that into the controller. So it cancels out damping, and so I need enough torque available to overcome friction damping. But other than that, I can have arbitrarily small, right? It's pretty cool. So why is this such a good controller? Well, what do you see inside here? It's not only simple to type in. That saved me a little typing, but I'm willing to type a lot if my controller works better. The interesting thing is that all I need to know is I need to be able to measure not even the energy, but the difference between my, sort of the distance between my current state and the other, and the homoclinic orbit. Now the homoclinic orbit, if you just expand the energy, it doesn't actually depend on the mass of the pendulum. You can change the mass of the pendulum. It still has the same homoclinic orbit. So this controller doesn't change depending on the mass. If I guess the mass completely wrong, it doesn't change my controller at all. If I guessed L wrong, like the length of the pendulum, well, first of all, if you guess L wrong, go buy a ruler. That one you should be able to get, right? Get a tape measure. But let's say I was imprecise in my measurement of the length of the pendulum. It only has a very subtle, so I can actually write it down here. The homoclinic orbit is defined as theta dot is plus or minus 2g over L, 1 minus cosine theta. That's the set of states, okay? So it has a mild dependence on L, no dependence on mass, okay? Gravity, again, you should be able to get that pretty well. And it's gentle in that too. Okay, so in practice, you go to type this in, and it works without very much tweaking on your robot. You change your mass a bit, it still works. Change your mass a as much as you want, it still works, right? So somehow, even though I was just doing this on the Lyapunov function, the form of that controller is very good. Yeah?
Did you use v dot equals vddx times f?
Yep. That's,
It looks like you just took the time.
oh, I just forgot to, I wrote it here.
Oh, okay.
It's coming out inside here, the E dot.
Okay.
It's inside this E dot. Everything I wrote is correct, right? So, but then the reason it looks mysterious, it doesn't look like what I did before, is that the chain rule puts that partial f, partial x. It only appears through here. Okay. We can make this work for the cart pull and the acrobat too. I don't know if I can make it work in 4 minutes or whatever. But let me get at least the cart pull working here for you. All right, in the sake of time, I'm going to set all the parameters to 1. Mass is 1, length is 1. I'm going to set gravity to 1, which I normally don't do, but that's going to save me some writing here. So, okay, so okay, if I do that, then I end up with my equations of motion, which were a bit to write down before. Now just, that's cosine theta, that's sine theta, right? Where the theta is the cart, is the pole angle, and x is the position of the cart, right? The second equation of motion right, so you remember the cart pole. Where this is x. This is theta. Okay? It has 2 equations, 2 unknowns, the theta double dot, x double dot, 1 force input. Okay. So, what's the intuition going to be for, what should I make for my Lyapunov function to stabilize this at the fixed point? It turns out I'm short on actuators, right? That's the whole point, is that I've only got 1 actuator to control 2 degrees of freedom. But the trick is going to be, I'm going to just try to worry about the pole first, okay? Let's think that the pole is just a pendulum, right? So why don't I go ahead and make think about the homoclinic orbit of the pendulum. I'll write my Lyapunov function against the pendulum, drive that to the upright, and then regulating the cart, it seems like it should be intuitive. I've got a force sitting here right here. I should be able to just put a little extra work in and get it back to the fixed point. Okay, so the idea to keep the algebra simple is to separate the dynamics of the cart and the pole. And it turns out you can do that in many surprising ways, okay? So I can, given 1 force, I can actually completely control x double dot, or I can almost completely control theta double dot. I can't control them both simultaneously, but I can pick one and think about that one. So to convince you, let's first just take this equation here and solve for theta double dot in terms of the others. So from that second equation, I get theta double dot is just negative x double dot c minus s, okay? If I stick that back in the first equation here, then I get f is 2x double dot plus negative x double dot c minus s times c, okay? minus theta dot s. Now, we've talked about feedback linearization. I can do a little bit of feedback linearization right here if I want, just to make the point, okay? Why don't I take f and apply the following controller, right? I'll choose my force to be 2 minus c squared, x double dot desired, minus sc minus theta dot squared s. If I stick that back in, I get x double dot equals x double dot desired. So this is partial feedback linearization. Why is it only partial feedback linearization? I've linearized that equation, but I've got another one sitting around that I haven't linearized, because I still have theta double dot doing its thing here, which is this negative x double dot c minus s. Okay? This one's still nonlinear, and I'm going to have to deal with it. I can always do this, because this quantity here is always non-zero, right? Kind of cool. If I were to then to do exactly the same thing, I'm more interested really in controlling this is like I'm going to control the cart, and I'm going to apply exactly the control I need to whatever no matter what the pendulum's doing, I can cancel that out. I can apply exactly the opposite force and take complete control of the cart. And it's not surprising that you can do that. What's maybe more surprising is that I can completely control the pendulum. Almost. Okay? So if I did exactly the same recipe, but I solved for x double dot first, insert that in, I can get a relationship between force and theta double dot. Okay? Since I'm short on time, let me just write it down here. If you choose this controller, then that implies theta double dot equals theta double dot desired, except when c equals 0, because that thing blows up. It's not invertible. When does c equal 0? Cosine equals 0 when I'm in that configuration or the opposite configuration. Right? So at the instant where the pendulum's right there, nothing I do pushing back and forth here can have an impact on the dynamics of the pendulum. And it falls right out of the equations. Okay? So that is also a feedback linearizing controller. This one that we had here, where we controlled the degree of freedom where the actuator was connected, is called co-located partial feedback linearization. And this one, where I'm controlling a remote, some other joint, is called non-co-located partial feedback linearization. And in general, these tools are very, very powerful when you choose to use them. If you have n actuators, you get to control roughly n things. As long as there's some dynamic coupling between them, you could sort of pick. So if you're a quad rotor, you got 4 motors, you get to pick 4 things you're going to control, right? Maybe you give up on controlling your total yaw, right? Or something like this, and we're going to see that play out too. Okay. If I'm a cart pole, I can control like the vertical position of my cart of my pole. You know, there's one term I get to control, and we'll see that play out. I guess I'm out of time, but we'll use this next time at the beginning to design a controller which descends a Lyapunov function and stabilizes the cart pole.